Watch a modern industrial lathe at work, and you see a seemingly flawless operation. A solid steel block spins, a hardened blade presses in, and the excess material glides away as a smooth ribbon. It looks effortless. Zooming in 1,000 times closer reveals a different reality. At the microscopic level, cutting metal is a continuous, violent act of localized destruction, driven by intense heat and friction. This invisible violence steadily wears down cutting tools. Across the global manufacturing industry, this microscopic degradation costs billions of dollars in replacement parts, lost time, and catastrophic component failures. To diagnose these unseen forces, engineers examine the waste material. They study chip morphology, the physical shape and structure of the discarded metal. That twisted scrap is a detailed physical recording of the cut itself. Protecting our tools and optimizing production requires us to read this metallic trash. We do that by breaking a cut down into two distinct phases, formation and wear. This diagram shows the initial period of chip formation, or IPCF, the exact millisecond a cutting tool first engages the material. The metal isn't being sliced. Instead, the tool acts as a wedge, crushing the atomic structure forward until it yields. As the tool pushes forward, all of that intense plastic deformation concentrates along a specific boundary called the shear plane. This glowing line marks the absolute limit of the metal's structural integrity before it breaks. Mechanical stress at this boundary generates massive thermal loads, triggering adiabatic shear bands. These are narrow, localized zones where intense heat causes the material to suddenly soften and fail. These cyclic waves of heat force the metal to snap and fracture into a rigid, segmented shape as it leaves the tool. This microscopic yielding dictates what we see on the factory floor. When cutting hard materials like titanium alloys, these thermal bands force the waste metal to break apart into highly segmented sawtooth chips. Cutting softer metals, or machining under cooler thermal conditions, prevents these intense shear bands from forming. The result is a single, continuous, smooth ribbon of waste. Whether a chip emerges smooth or heavily serrated, its morphology is a physical mirror of the thermal physics occurring at the exact moment of separation. Once the chip forms at the shear plane, it immediately enters the tool-chip interface. Here, the superheated metal shaving is violently forced upward, dragging across the rake face of the cutting tool. This sliding contact creates immense friction. The temperature transitions along the face of the tool create the perfect environment for rapid degradation. This diagram illustrates the built-up edge, or BUE. BUE is a wear mechanism that occurs when extreme friction and pressure cause fragments of the heated chip to melt and permanently fuse to the cutting tool. This bonded metal accumulates, altering the original geometry of the blade. The blunt, jagged mass ruins the surface roughness of the manufactured part below and accelerates tool fatigue. The material being cut actively mutates and destroys the tool's edge, changing its geometry through intense pressure and heat. Engineers fight back against this friction by manipulating specific cutting variables to force the metal into a safer, more efficient chip morphology. Advanced lubrication strategies, ranging from cryogenic cooling systems to simple coconut oil, drastically reduce chip thickness and eliminate the dangerous serrations commonly seen in dry milling. This schematic compares a standard flat tool face with a micro-grooved surface. Altering the physical geometry of the tool with these textures limits the contact length, the actual physical area where the superheated chip touches the tool. These carefully designed surface textures physically force the metal chips to curl tightly and snap off. They evacuate the cutting zone before they wrap around the tool or melt into the blade. Reducing that contact length directly lowers the thermal load on the tool. This preserves the structural integrity of the metal, allowing a single blade to flawlessly execute thousands of cuts. By utilizing specialized fluids and microscopic surface geometries, engineers dictate the exact shape the waste material takes to neutralize the violent forces of the cut. Back on the factory floor, these flying metal shavings represent highly engineered, predictable shapes resulting from controlled physics. Modern optical monitoring systems now capture these chips in midair to analyze their size, shape, and chromaticity. Chromaticity refers to the specific color changes a metal undergoes when exposed to intense heat, acting as a direct temperature readout. Processing this continuous stream of morphological data allows artificial intelligence to predict tool life. The system can adjust cutting parameters in real time, correcting thermal imbalances long before a tool fails. Mastering the micromechanics of the chip allows manufacturing to evolve from brute force cutting into a data-driven predictive science that prevents failure before it happens.